So thank you for the introduction. I start now with the presentation. The first deep dive is on positioning, and here it is in and outdoor positioning with 5G and GNSS. I start with an introduction. What you can see here is a slide which comes more from GNSS and some general challenges when you go in closed buildings, for example, but the same is valid indoors. What you can see on the right side are a few satellites and some houses, and you can see that some signals are blocked. So one challenge is that you have enough signals to do positioning. The next challenge are the reflections, scatterings, and so on ongoing on that surfaces and edges and so on. So the estimated distance is too high if you receive only reflected or scattered signals, for example, and then you have a large positioning error. And in the video, you can see an example from our simulation testbed with SENAV and Spirent. You can see now only reflections. Now everything will turn on quickly. So you see now a lot of rays in the air, and you can imagine it gets very, very tough when you go indoors and you have a lot of things indoors. So this is a main challenge. One solution that we present and that we are focusing on is hybrid positioning in terms of hybrid systems and hybrid methods. Hybrid systems, for example, as in the example on the right side, you can combine satellite navigation with 5G in future. So that means that you have more signals you can use and should have a better positioning in the future. For example, even to have autonomous drones here that can bring, for example, some stuff when there's an emergency. This is a project ongoing. And hybrid methods, that means that we have classical methods using Bayesian filtering, for example, tracking of signals, but we combine them with AI and have then a hybrid positioning solution in that case. How can that go? For example, here with GNSS and ultra wideband, with GNSS, you have a lot of satellites here in range, for example. Now, the first thing you should do is do an anomaly detection to see which satellites you use for positioning, because you have a line of sight to them. So the signals are not reflected or scattered or anything. And the same you can do with signals that you use on, for example, even indoors, like 5G and ultra wideband. You receive some channel impulse responses, for example. You do also an anomaly detection to see which signals you can use very easily for positioning and which signals are more challenging, but maybe you still want to use them then in a hybrid positioning solution. But then there's again a very, very big challenge, and I hope Max can help us now, because we need first the 5G signals indoor for positioning, and this Max will tell you now.
Thank you. So before I come to the question how we get 5G positioning up and running for methods like this hybrid approach, I want to spend one slide on the question, what is this 5G positioning at all? Because sometimes there's some misconception, and 5G positioning is not really a new positioning method, and it's also not a new positioning system. What you see here are two columns on the left side, RUT dependent, and RUT dependent means dependent on the radio access technology of 5G. So these are positioning methods that use 5G signals and a 5G network for positioning. This can be time-based, angle-based, or hybrid positioning methods. On the right side, you also see RUT-independent positioning approaches that are also supported by 5G. So they don't rely on 5G signals, and also sometimes not even on 5G infrastructure, but they incorporate, for example, assisted GNSS, Wi-Fi, terrestrial beacon systems for positioning. So in fact, if Jochen spends a click on the slides, I think the core message is 5G positioning is a new approach to apply multiple positioning methods, and for that it also incorporates complete non-5G related 5G positioning positioning solutions, non-5G positioning solutions. On the next slide, I wanted to have some bullet points what opportunity this means, because for positioning, we are confronted with multiple various use cases, different use cases. And with 5G, we have multiple positioning approaches to tackle these use cases. That's great because different use cases come with different requirements, and different positioning methods have their individual benefits and drawbacks. So we can match the use case with a positioning approach if we have a lot of approaches available with 5G positioning. Then there's a word, Gateway Mobile Location Center. That's in fact a part of a 5G core network. And for a client who wants to use positions of mobile devices, this is exactly the module that provides this positioning service and this positioning information. And it's one service in a 5G network that provides positioning information for mobile devices for various methods. So there are not multiple access points. You don't need multiple systems and integrate multiple systems. There's one interface for that. And of course, 5G is first of all a communication system, and positioning is an add-on to communication. So that means potentially you can have lower total cost of ownership if you combine your communication and positioning approach. The thing that I currently wouldn't expect is that a 5G positioning solution is cheaper than a positioning only solution if you break it down just on the positioning aspect. But if you have had a lot of use cases, also use communication services, then this combined approach can have benefits. Obviously, there are certainly also obstacles right now, and the main obstacle is availability. First of all, there was positioning in 4G, but positioning for industrial use cases is pretty new for 5G. New topics don't have necessarily the highest priority in standardization and also in the availability of commercial equipment. And then 5G positioning will mainly be used in private networks. And this means that these private campus networks that are also a new topic are a requirement for precise positioning. What you see here is how we tackle the early evaluation of 5G positioning. There's a video on the top left of the screen. You can see our link testbed, our 5G Bavaria testbed there. And we have an AGV that is driving on a course and that is tracked by 5G downlink TDOA positioning. So the method is what you can see on the right. We have several radio units. They are transmitting positioning reference sequences, and a mobile device, the UE, can capture these signals, calculate the time of arrival, and based on the time differences, the position of the UE in the test center is calculated. Now, with another click, we have some additional text. What's important, we're not building our own 5G system here. We are focusing on the relevant positioning aspects to evaluate questions like how is the 5G spectrum suited for positioning, how well do 5G positioning signals work, and perhaps also what considerations about the deployment do you have to make if you don't use 5G only for communication, but also for positioning. And this enables early access to the evaluation of use cases. And we have extended this testbed also to the outside, and then we could evaluate hybrid 5G and GNSS positioning, just as my colleague Jochen showed you on his slides. Another topic we're trying to tackle with this early access is how to do positioning in complex environments. And complex environments are a challenge if signals are shadowed and reflected. And the machine learning or AI-based methods that we try to apply to tackle these challenges, they are relying on data. And such an SDR-based approach has the benefit that we get real-world data to evaluate and develop new approaches to tackle positioning in complex environments. And I think that's exactly what Jochen will tell you something more about.
Exactly. Thank you, Max. So thanks to Max, we have already signals, we can do measurements, and we did large measurement campaigns last year. And based on these measurement campaigns, we started to realize our research pipeline that you can see here for AI-based or assisted positioning, especially in complex environments like you have in industry cases. What is here? So we see that first it starts. Okay, not showing. First, we start with signals on the left side. We are sampling signals, and then we do this anomaly detection like I showed in the beginning to identify which signals are line of sight signals and which are non-line of sight signals. And multipath is the normal, of course, in indoor environments, for example. Then we do positioning. And after positioning, there comes an uncertainty estimation. Why is this necessary? If you have a data-driven approach, that means that you have trained a model using AI to do positioning. This model fits very well to your environment, but if you have big changes in the environment, the model will no longer fit. So it's important to know where, for example, in the room or in the big hall, you can do positioning very well, so more green and blue, and where your model does no longer fit because, for example, you have now big obstacles there that change the propagation of the signals. That if you have changes, you need to learn that changes doing simulations or collecting measurements. We call this continual learning. So you have a new model you can do positioning with. Now let's have a closer look. So first is anomaly detection, as I said. You see here an example of a channel impulse response or of multiple channel impulse responses from some stations here in the link. And exemplary here for the one here, you see here the channel impulse response. So now signal was blocked a bit. So the channel impulse response is very noisy. Now you have a bit of line of sight. So you have almost a peak. Again, no line of sight, it was noisy, and now you have a peak again. Yeah? So you see, depending on if you have a line of sight or not, your channel impulse response varies, and it also varies depending on where you are in this environment. You see here the environment with shelves and, for example, a forklift here in our link testbed. What we do then, for example, is we doing a feature-based analysis. That means here in this case, we have, for example, 4 features: the correlation maximum of the signal, the echo density energy index, energy decay index, and you can see different things with these features. Here, for example, correlation maximum, I guess it's easy to understand what it is. Here, the value is very high, and you have the red area, you have a line of sight. And here it's very low because the signal here, for example, from here to here is blocked by the shelves. So it's very low, and you have blue, there's an anomaly. And we showed in papers that correlation maximum and echo density can show shadowing, and energy index and energy decay indicate a multipath like you have here, for example. So it's not only the shadowing, but here are also differences here in the back of the shelves that indicate the multipath propagation. Then I said we do AI-based positioning. That means we have data-driven methods using channel impulse responses or, for example, time difference of arrival to achieve accurate position estimates. We have here an example already with a corrupted model. What does that mean? We measured in the environment here with absorber walls, a van, and some obstacles. And then we put the van from down here to there where you see it on the picture. So first it was here, then it is here. And what happens now, the propagation of the signals changes near to the van here. And also here it changed because the van is no longer there. So the model is a bit corrupted. We want to have an accuracy in the range of below 50 centimeters. So we had sometimes a mean errors of, for example, 30 centimeters. But with the corrupted model, you no longer achieve the accuracy. So you need first to know that your model is corrupted. That is the uncertainty estimation. Of course, you have uncertainty of data like sensor noise, but for us important is the uncertainty on unknown data because of changes in their environment. When you detect that there are changes, you can collect more measurements during the process that you have anyway, and then learn again, for example, by doing fine tuning with a few measurements in the area again. to achieve again the accuracy that in the range of, for example, 30 centimeters. So this is then the positioning and the uncertainty estimation. We have detected the model is corrupt. We measured new data to do continual learning, and then we can do positioning again with the signals where we apply at first, for example, anomaly detection. And that's already the last slide of the presentation. And I thank you very much, and also my colleague Max for presenting with me together. And we are happy, of course, now to go with that next year into the link hall, realize live demonstrators with the positioning and the machine learning based positioning for complex environments to show how positioning works in such environments and in such complicated use cases, like when you go with a forklift, for example, between shelves and so on. Thank you very much, and I'm happy for questions.